Hello and welcome to our Engineering Tributes. Now this is a segment of the show where we give a tribute, a shout out to an engineer, researcher, or mathematician that has bettered society as a whole with their research. And today we're taking a closer look at Werner Heisenberg. So we're going to learn a little bit about who Werner Heisenberg was, some of the concepts that he came up with, and a little bit about the man himself. So let's go ahead without further ado and dive in. So first things first, Werner Heisenberg is actually best known for his Heisenberg uncertainty principle. So this is the idea that we can't know a particle's speed and momentum, okay, at the same time. So we can't tell where the position and momentum of a particle is. So we can't tell where a particle is and its speed at the same time. We can know one or the other, but we can't know both. And this is actually a really important discovery because it laid down this sort of underlying uncertainty in the universe, in the idea that we can never deterministically know the events that are going to happen. So for example, the weather is a stochastic process, right? It's very random. It's very hard to predict because small changes can create huge variations in the weather. And that's often why the weather reports are off by quite a lot, if you've ever seen that happen. You know, if the weatherman's like, oh, it's going to snow tomorrow, and then it doesn't snow. Well, it's actually because it's very hard to predict. But there's always been this idea that if we could collect enough information, if we could know enough things, then we could actually predict exactly, like, where is it going to snow, right? The idea is that if we collect enough information, maybe we can determine everything that will happen in the universe. That's a deterministic approach to the universe. But this uncertainty principle kind of shattered that concept, the idea that we could know enough to predict anything, because we cannot know at a fundamental level a particle's position and momentum, and so that kind of like broke a little bit some of this argument that the universe is deterministic and we can figure these things out. At a fundamental level, some portion of it is random, and we can't know things, right? But it hasn't completely deterred the deterministic view, but it has definitely shaken its ground a little bit. So very, very important principle. So for this discovery, Werner Heisenberg actually won the 1932 Nobel Prize for his work in quantum mechanics. So congratulations, Werner Heisenberg. He did some fantastic stuff. He also studied hydrodynamics and made some very important contributions to turbulent flows. So there are different kinds of flows. There's laminar flow and turbulent flow. Laminar flow, it has to do with water, right? So if you've ever seen water coming out of a hose, it normally looks pretty nice and clean, right? If you've seen like waves in the ocean, you've probably seen that they're kind of more, like they kind of slosh around a little bit more. They don't look very nice and straight. And there's a reason for this, right? Those are the two different kinds of flows, the laminar flow and the turbulent flow. The turbulent flow, we're not quite able to predict what the flows look like, okay? And there can be some sort of like little eddies and things that show up, some little spirals in the flow that kind of can show up and make the whole process kind of random. And so there are two different kinds of flow, and turbulent flow is the more random kind of flow. And that is actually where Heisenberg made some of his contributions. So he even you know, in his study of flows, turbulent flow, he studied the more random of the two. And finally, he was a pianist, so he really enjoyed playing piano and classical music. So that is Heisenberg. Thank you so much for your principles. Now we're going to transition into our Maker Highlights. So this is my favorite segment of the show, where we get to highlight a couple of projects that students have been working on either here at Zen Maker Lab or submitted to us through our website. So of course, if you would like to see your project here and you're not enrolled in one of our Maker Lab programs, no worries. You can always send us a picture of your project or whatever it is that you're working on with a description. And if we like it, we'll put it here on the show. But let's go ahead. We're going to take a look at two projects today by the same student, Liam. So let's go ahead and dive into Liam's projects for today. So first up, we have Liam's bearing. Okay, so this was a design that was a concept of Liam's. He was working on a challenge that I give a lot of my students, is to design a 3D printed bearing. This can actually be rather complex. So let's go ahead, let's take a look at Liam's implementation of the bearing and see if there are any ways that we can improve upon this design. Okay, so we see that there are a number of different balls here, and these balls are making up a ring. So one thing that I do really appreciate about this design is we are using the duplication tool. We're using the duplication tool, and Liam actually looked to make sure that there would be enough room around this ring to actually house all these balls, but let them kind of roll freely. So that's good too. And we can see that there are at least two distinctive parts, right? We've got this part, right, the balls, and then we've got the outer piece here that disc can kind of rotate inside of. So that's good. However, we do have a little bit of an issue with the with sort of this ball shape. So when we're designing things to be 3D printed, we want to really be careful of the slopes that are in our designs. So if we have something that is very close to being parallel to the bed, but isn't actually on the bed, it's like raised slightly, that can cause some issues. So when we are printing a sphere like this, typically the bottom ends up being pretty rough. So we have to be really careful when we're designing something to be 3D printed. If you want it to be nice and smooth, nice and round, you need to, the best thing usually is to either modify your design slightly, or in this case, maybe even cut that ball in half and then glue each one individually together at the end. So that could have been one way that we could improve this design. We can also see that I think that these balls aren't supposed to be touching, but they are slightly touching on some of these areas. So another way that we could improve this design, rather than not just only cutting these balls in half and flipping them over so that they print, something like this and gluing them together, we can also actually separate these balls out. Okay, so rather than having them print all like this, maybe we just sort of move them back a little bit more, so that they're not actually touching. Because if they're touching, they're going to print together. Like for example, these two are definitely touching here. So if we printed this out, this would be one rigid piece. Okay, so we want to be really careful when we are designing things to make sure that they're not touching here. Something else with ball bearings is typically they are enclosed, and here we have this ring, or these balls are not actually enclosed. They're not like trapped inside there, and can only move around the outside of or move around in a circle, right? We can actually pull these bearings out. So normally I think we would need some sort of top cover to sort of hold those balls in there. And lastly, I can see that the bottom of this piece is actually connected. So this is all one piece. And if we're designing a bearing, typically what we have is we have an inner ring, we have an outer ring, and then the balls are there to allow that inner ring to rotate separate from the outer ring, or the outer ring to rotate free of the inner ring. So there's those two different rings. But here, because those two rings are attached, the only thing that's actually able to really move is the ball bearings. But maybe that's okay. Plastic tends to have a very low static or a very low friction coefficient. And so these two pieces could probably glide against each other with a minimal amount of friction. But again, because we're 3D printing, we have these little ridges, which actually, in many cases, add some extra resistance. So that's something to be aware of. So let's take a look at the next project that Liam's been working on, Liam's spiral. So this is a spiral that is actually based off of a torsion spring. So let's take a look at this. So this is a pretty cool design. The idea is that we can maybe wind up the center here, and when we let go, it's going to rotate a little bit. Okay, it's going to oscillate back and forth. And this is known as a spiral torsion spring. I can actually pull this up for you here. Spiral torsion spring. We can look at some images. So this is what Liam was working on, was designing a spiral torsion spring like this. And these are actually typically found in a lot of wind-up watches. So you'll have one of these spiral springs and then a big mass wheel that moves around, and they oscillate at a specific frequency for the clock to actually run correctly. And so that's what Liam is working on here. And it looks pretty good. Some things that we could maybe take another look at is maybe the thickness of this torsion spring. So we can see here that these are very thin, and this torsion spring, it might be a little bit thick, right? We might be able to improve it by making it a little bit thinner. Something else is it is not a perfect spiral. This was drawn by hand using the scribble tool. So if I open the scribble tool here and I try and draw a spiral, I can do maybe a pretty good job, but it's hard to get it perfect. And there are different kinds of spirals. So there are spirals that grow or shrink. Anyways, so maybe there's a better way to automate that spiral using that. But great job, Liam, on these two mechanical maker projects. Fantastic work. Don't go anywhere, because up next we have an interview with Nagayan, who is a civil engineer in training. So stay tuned.